Okay, so now we're going to look at spontaneous redox reactions. If you'd watched the original one of the videos I asked you to watch earlier, with revising redox, you will have seen these, and this will help. Okay, so if we look at the direct transfer of electrons, in other words, we transfer electrons from one substance to another without directly, so the two substances are in contact with each other. So what we have here is we have a copper sulfate solution inside of which we put a piece of zinc metal. Now these will react spontaneously because the copper 2 plus ions, which are in the solution, these ions over here, desperately want to be copper metal. Okay, they do not want to be copper ions. The zinc, on the other hand, is going, yeah, it's okay, you can take my electrons, it's not a problem. So the zinc has 2 electrons it can give away. I only drew 1 here, but it doesn't matter, it's the same concept. So it gives 2 of its electrons to the copper, and the copper then becomes copper metal. So as a result of it giving its electrons away, we end up with Cu2 plus ions and copper metal. Now they can't stay where they were, so the Cu2 plus ions come off the piece of zinc metal, and the copper forms at the bottom of the solution, and it's a very fine powder. Okay, so what happens is the blue solution now turns colorless because the blue was there because of the copper ions, which are now gone. They've become copper metal. The sulfate ions didn't do anything. They're a spectator. And the zinc metal will eventually disappear. It'll eventually completely disappear if we have enough copper sulfate solution. So this is a direct transfer because we've taken electrons from the metal and we've transferred them to the copper. Okay, so we get copper metal in zinc sulfate solution. So if we look at it from a half reaction point of view, the zinc goes to zinc 2 plus 2 electrons because it gave away its electrons, so it's oxidized. The copper 2 plus becomes copper because it was reduced, and here's the overall reaction. Now this was direct transfer, it all happened in one container. However, if we can take those electrons and we can force them to go through an external circuit, so in other words, I can take this reaction and make it happen in one place. We take this reaction, we make it happen in another place, and then we force the electrons to travel between them. We can create a cell, we can create a battery. Okay, so if we look at the construction of a voltaic cell or galvanic cell, they're both the same. A cell in which chemical energy is converted chemical energy to electrical energy. We've already done that once. Electrolytic cells, electrical to chemical. Now we're doing the other way around. It also has to have a self-sustaining electrode reactions. In other words, these have to be spontaneous reactions because we want them to create the electricity. We don't want them to use the electricity. So how does it look? Well, if we look at the structure, we have 2 half cells. Half cells, each part of it does half a reaction. So if we look, we have a half cell. This is one half of what's going on. There's the other half of what's going on. But you can't have one without the other. Each half cell has an electrode and each half cell has an electrolyte. Take careful note, we have an anode and a cathode, but the anode is now negative, the cathode is now positive. It's the opposite than an electrolytic cell. Okay, you have your electrolytes, which need to conduct an electric current, and we're going to talk about what each of these are going to be made out of. We then have a voltmeter, though here you could also have a galvanometer, or maybe they're going to put a light bulb in. Okay, it doesn't matter, it's got to be something that indicates that a current has been formed. The 2 electrodes are connected to each other via the external circuit, and the 2 beakers are connected by a salt bridge. We're going to talk about functions of everything in a second. The electrode at which oxidation takes place is the anode. That hasn't changed. Same as with an electrolytic cell. The electrode at which reduction takes place is still the cathode. Same as with the electrolytic cell. The anode now is negative because it's where the electrons are deposited and the electrons leave from. Okay, so the electrons leave from the negative. The cathode needs to be positive because it's where the electrons need to go. The electrons must be attracted to the cathode. Very, 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 very important. The electrons must be attracted to the cathode. So what I'm telling you is that current will always flow from the anode to the cathode. Okay, so from the negative electrode to the positive electrode. Always, always, always. Okay? The two half cells are connected by something called a salt bridge. The salt bridge is a tube which is filled with a saturated salt solution. It can be potassium chloride, potassium nitrate, sodium sulfate. Do yourselves a favor. You really only need to know that it's potassium nitrate, KNO3. Chlorides can be a little dangerous to use because, not that it's going to explode, but because sometimes you'll end up using a chloride, which then results in you forming a precipitate, and you don't want that. You don't want anything that can't dissolve. Okay, and then we fit the ends with the porous plugs like cotton wool so that the liquid can move in it, but we don't want the liquid to all come out of it when we turn it upside down. The galvanic cell uses indirect redox reactions because the chemicals that are being oxidized and reduced aren't actually in physical contact with each other. So the zinc and the copper, if that's what we're looking at, don't physically touch each other. Okay, so it's indirect. If we now go back to the example, we used zinc and copper just now. We're now going to set up a very simple zinc copper cell. We're using the zinc copper cell to show you how it works, but really they can ask you anything. All right. The zinc copper cell will then consist of a zinc half cell and a copper half cell. So we're going to have two containers. One's going to contain zinc, one's going to contain copper. The zinc half cell consists of a zinc electrode in a zinc salt. The electrolyte must have whatever the electrode's made out of. All right? Zinc sulfate, zinc nitrate, zinc chloride, etc. You can just keep everything as sulfates. The copper electrode must also be in a copper salt. Copper sulfate, copper nitrate. Keep them all the same. They don't have to be the same, but make your life easier. Okay? The sulfate ion is a spectator ion. It's there because I can't have zinc 2 plus ions just randomly running around. They don't exist. They have to come with something. So the sulfate is what it comes with. Okay? So this is what happens. Basic setup again. So we have the anode, all right, over here, where oxidation takes place. So the zinc gets oxidized, and the zinc becomes zinc 2 plus. Let's just get rid of that there so you can see it. All right, so the zinc gets oxidized. The electrons move through the cell, get to the other side. We now have a copper cathode where reduction takes place. Okay, so the copper becomes copper metal. The anode decreases in mass. The cathode increases in mass, always. Okay, always, 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 always. Then we have the salt bridge, which has ions in it, which maintain electrical neutrality, keeps the electrolyte solutions neutral. Okay, very, very important. And it also completes the circuit, because it's an electrical circuit, it has to be complete. Now, at this juncture, there are two videos that would be a good idea for you to go look at, because it really does explain how a salt bridge works, which is a really nice explanation, and it gives you a nice visual explanation of what's going on. Okay, so it's there's the galvanic cell part 1 and there's the galvanic cell part 2. They are in teams. If we look at the cells and we look at the equations that are taking place, so we have zinc becoming zinc 2 plus, just like with the direct transfer. We have copper becoming copper, so the zinc copper 2 plus becomes copper, and we add them together, and here we go. Copper 2 plus becomes copper because it was reduced. Zinc becomes zinc 2 plus because it was oxidized. I do not care about what ions were in the salt bridge, and I do not care about the extra ions that were in the electrolytes. Those are all spectators. You will never, ever, 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 ever have to put them in these equations. It is way too complicated, so we're not going to worry